Thank you very much, Professor Govind. It's a pleasure to be here. Thank you for having me. My talk is on imagining a next generation superoptimizer. I hope the title sets the expectations correctly. Let me elaborate. Please focus on the word imagining. I'm largely going to be painting a vision. I am going to draw on a work that has been done by other research groups, and I'm going to talk about work that we have done in this direction. It's a large problem, and there are pieces that are that are kind of that I expect to come together in the future, and that's what this talk is all about. My affiliations are Graviton Research Lab and IIT Delhi as listed here. I also run a startup called Compiler AI Labs, but it was like too many affiliations on a single slide and things like that. But I just want to say that all of these things basically kind of do this. I mean, are working on some aspect of optimization, super optimization, and things like that. Just different vehicles to kind of achieve the same goal. And I'm going to talk about that goal today, and I hope I'm able to get the message across. So you may have noticed that compilers have been growing in complexity over the past 3 decades. The chart demonstrates the number of lines of code in the GCC compiler over time. Starting from 1992, the number of lines of code has increased linearly, basically as fast as humans could develop it. Today, GCC stands at over 22 million lines of code, which is an astounding amount of complexity, much of which is due to its code generation and optimization logic. At this point, I'm sometimes asked about this dip at around 2016-2017 in the number of lines of code. And this is because a garbage collector named Boeing was deprecated at this time. There's nothing fundamental here about this dip. But as you can see, I mean, it was, we covered up that dip pretty quickly, and, our complexity is much more than what it was even after the dip and things like that. Now, I don't think this is a very happy picture. It is a happy picture for compiler developers because it gives you job security, but I don't think it's a happy picture from the point of view of how compilers are progressing over the decades. And if you think that it's only GCC, that's not true at all. LLVM is another important compiler architecture, infrastructure that I'm sure most of you know, that has risen to popularity both because of its cleaner abstractions and permissive license vis-a-vis GCC. Indeed, LLVM developers have distinct advantages over GCC developers by virtue of starting late and thus leveraging modern tools and techniques and also avoiding known mistakes. Even after all this good engineering or better engineering, the development model hasn't changed, and we see a similar growth in complexity for LLVM too. Here I show the lines of code in LLVM's core components, mostly the include and lib directories, in LLVM over time. Once again, we see a linear increase in complexity that is showing no signs of slowing down. The total lines of code in LLVM's core components stands at around 4 million lines of code today. It is thus no surprise that we witness some kind of a fatigue in compiler development. Students are afraid to enter this space, as even the best contributions may seem incremental in this setting. And it is not just about the new entrants. This example of a conversation shows how an existing compiler developer can feel disinterested in implementing yet another improvement that optimizes a particular coding pattern. A compiler requires millions of such incremental improvements to become and remain a top quality production compiler. However, each improvement involves laborious design and implementation, which is the root cause of the growth in compiler complexity over the past 3 decades, and keeps the pace of compiler development slower than desired. I want to clarify that I'm not at all saying that compiler development has saturated. In fact, my next couple of slides motivate through examples that there remains lots of headroom for a compiler to improve. We just need a better development model. A simple implementation of the strlen function in C is shown on the left, and an optimized implementation as available in the glibc library is shown on the right. The glibc implementation first aligns the input pointer to a 4-byte boundary in the first loop over here, and then in its second loop reads 4 bytes in one instruction, and checks whether any of those 4 bytes are null by using this clever use of masks, arithmetic, and logical operations. This kind of things you will find in literature like A Hacker's Delight and things like that, where you can say, oh, how to do this thing using fewer number of instructions. If the expected size of the input strings is long, then this implementation can offer a 3 to 4x speed up over the simple implementation shown on the left. However, today's compilers are unable to perform such optimizations automatically. Here is another example. On the left is a functional specification of the strlen function. The functional language is our own, so don't read too much into it. It is similar to OCaml, but perhaps not identical. The functional specification just says that a string is formed by a nil terminated list of characters, but does not specify how that list is implemented, whether as an array or a list or something in the middle. On the right is an implementation of strlen in C that uses a chunked list to represent a string. It uses the same trick of reading 4 bytes in a single read, but it also stores a string non-contiguously to save space through sharing. It can be shown that these two implementations are mathematically equivalent. However, this seems well out of reach of today's compilers. There are many other examples of hand-coded optimizations that are in everyday use, but are either out of scope or poorly supported by a compiler today, even after decades of development. Complex rewrites involving SIMD vector instructions are one example. While ideas like superword level parallelism, SLP, tackle this problem in a significant way, there's still a lot of performance that is left on the floor with vectorization. The array-based strlen implementation that I showed on the previous slide is one such example of vectorization that a compiler cannot do today, even after all the years of development in vectorization. Data structure selection is another one that perhaps requires a higher level spec than C-like syntax, but a compiler is unable to do today. And there are many more, not necessarily present on the slide. I will not go through all the examples on this slide, as I don't think there's any controversy on the fact that there's much more that is possible than what compilers do today. One potential solution to this problem is to try and get machines to help us in this compiler development task. An overwhelmingly large fraction of the compiler complexity is its optimization logic. So if we could get the machines to automatically identify optimization opportunities, that would relieve the human programmers of this complex task and could potentially make the compiler development process faster. Here we have two sets of algorithms. One set are the inductive synthesis algorithms that use certain heuristics and search strategies to automatically propose candidate solutions. You can imagine that these inductive synthesis algorithms are approximate. For example, they may be based on machine learning techniques. And so, the candidate solutions may be incorrect. However, a compiler cannot tolerate an incorrect optimization, and so we use a validator, also called an equivalence checker, that checks every candidate solution. This is the second set of required algorithms in this design. The equivalence checker checks the candidate solution for equivalence against the program specification. If it is able to prove that the two are equivalent, we obtain an optimized solution. On the other hand, if the equivalence checker is unable to prove that the program specification and the optimized assembly implementation are equivalent, it should hopefully generate a counterexample that demonstrates this inequivalence. A counterexample here is just a program input that would cause the specification and implementation to behave differently. This counterexample can then be used by the inductive synthesis algorithms to appropriately fine-tune their search. So better candidates are generated in the future. This vision has been painted by several researchers in a common theme of work called program superoptimization. The name superoptimization was coined by Henry Massillon in 1987, where he was interested in finding the optimal implementation for a given problem using machine power. Now, the term superoptimization is used for a technique that uses machine power to discover optimizations. even though it may not necessarily be searching for the optimal solution. For inductive synthesis, there are several algorithms that have been proposed, starting from brute force enumeration, stochastic search, learning from examples, mutation-based learning, constraint solving, and many more. Recently, the breakthroughs in neural networks and large language models have made them a very promising approach to try and attack this problem. And I will talk about one such recent effort in more detail. Meta's LLM compiler is an LLM that has been trained and fine-tuned for 3 distinct tasks. Emulating a compiler involving specifying as input the unoptimized LLVM IR, the optimization flag, and obtaining the output IR and or assembly. The second task is for tuning compiler flags for optimizing code size. They give as input the program as unoptimized LLVM IR and request the model to predict the required optimization flags for code size reduction and the output LLVM IR. Finally, the third task involves a task where the model is trained for disassembling assembly to LLVM IR, which basically means it's the inverse function of a compiler or a decompiler. I'll share more details about all these 3 efforts in my next few slides. Here is the prompt used for LLVM to LLVM compiler emulation. The prompt says, give the LLVM IR for the following code when optimized using this set of optimization passes as given to the opt tool in the LLVM instructor. The prompt also says that what is the input instruction count. So the input code has instruction count XYZ and binary size ABC bytes. And then it expects the LLM to answer that the LLVM IR that you output will have instruction count DEF and binary size GHI bytes. And then it will output the optimized LLVM IR. Now this is the prompt and the answer. If you are aware of how LLMs are or how neural networks are trained, you just fill up the right answers for these dashes and train it over lots and lots of examples. And then you magically start expecting that it starts giving near approximately correct answers for unseen inputs. Here is another example. Here is a prompt for LLVM to x86 compiler emulation. Similar, give the assembly for the following code when optimized using opt passes. The input code has instruction count blah and binary size blah. And the answer that is expected is the assembly will have instruction count blah and binary size blah, and here is the assembly. What are the results? The results show that pre-training and fine-tuning helps significantly. After pre-training and fine-tuning using the prompts and answers that I showed you in the previous slide and lots of different correct answers, we see that 95.6% of the code that is generated by the LLM compiles. That means it's syntactically good LLVM. 20% of the generated code is an exact match for what LLVM produces, which I think is a phenomenal result. You can also see that before fine-tuning, so I'm looking at the last row here. You can also see that before fine-tuning, the exact number is near 0. So if you look at these numbers here before fine-tuning, so the LLM compiler starts with the code llama LLM, which has not been trained with all these prompts and things, and so the results are much poorer when it's not trained. But if you start training it, then it starts giving better results. But you can see, I mean, one thing that I noticed here is that the compiles value, which is 5.4%, is still pretty respectable, pretty high. So which basically means that Code Llama has already learned the LLVM syntax. It just doesn't know how to do compilation and decompilation, which fine-tuning allows it to learn. Here is another task that they did in their paper, which is an auto-tuner. And here they try around 5,000 random sequences of passes per program. So recall that the second task was not about actually generating the LLVM IR from the blind or magically. The idea was just give me the right set of passes such that I can minimize the code size. And you know, the OZ flag, I believe, yeah, the OZ flag is used for minimizing the code size that is given by default by LLVM on WinGCC. But it is well known that the code size that's produced by OZ is not necessarily the smallest that you can get. And if you use a different set of command line options, then you can get a much better answer. And so the task here is what is the right set of command line options such that I get the minimum code size. I don't trust OZ, I want to do better than OZ. In this task, notice that I'm just training the LLM to predict what passes I need. I'm still using the compiler to kind of do the optimization and the code generation. And in this result, I think the primary result here is that it produces a 7.1% reduction in binary size over -OZ after training and pre-tuning on the correct set of optimization flags. So what is the prompt here? The prompt is, tell me how to optimize this LLVM IR for object file size, and you give the LLVM IR. And the answer that you expect is the code has object file size of, so you expect the LLVM to predict what the object file size will be in x86. So sorry, you ask it to, you expect the model to predict what the code size will be for the without any optimization. And then if you apply this optimization, then what will be the code size? And what will be the eventual code that will be generated? So all these tasks we expect the LLM to help us with. What are the results? Evaluated on an embedded benchmark suite called MyBench, MIBench, and with a 13 billion parameter LLM, this LLM generates object files that are shorter than -OZ in 61% cases. But it also sometimes generates object files that are larger than -OZ, and that happens in 12% cases. But there's an easy solution to that. You just run with -OZ and with the LLM and just pick the smaller one if you're interested in the smaller size. For some benchmarks, the improvements are as high as 13% extra reduction in code size. That's, I think, huge. The improvements with the 7 billion parameter model are often higher than the improvements obtained with the 13 billion parameter model. So it seems like the bigger the model, the better the results, at least at this scale. The third task that they did was disassembly or decompilation. Learn the inverse relationship for the command clang-xir, some C file, -o, some assembly file with the -s option. The prompt here is disassemble this code to LLVM IR, and you give the assembly code, and you expect the LLVM IR to be the answer. The LLVM is optimized. So to train this particular disassembly task and to avoid redundancy, what the authors did was they optimized LLVM using the -OZ flag before loading it to x86 assembly. So the idea is that you take some LLVM, you generate x86 assembly, you take the x86 assembly and put it in the prompt, take the LLVM, put it in the answer. But as we all know, there's redundancy. There are many different LLVM programs that give the same x86 assembly. So we want the one that is, canonical, and for the canonical version, they just use the one that has the smallest size, let's say. And how do you know what's the smallest size? They just use a -OZ flag. Okay, so now the question is, how do we know that these outputs are correct? So they use a data set of 4.7 million samples. They have a context length of 8,000 tokens for the input assembly and 8,000 tokens for the output IR. And the question is, how do they do the equivalence check? Well, they do round tripping. So what they do is they convert the disassembled LLVM IR back to assembly using Clang and check if we get an identical syntactic assembly. And if we do, we declare success. If we don't, then we declare failure. These are the results for the disassembly task. For 936 out of the 2015 input assembly programs, the output LLVM IR is well formed. So it's generating correct syntax LLVM IR for a large fraction, around 50% of the cases. Further, 14% of these programs produce exactly the same assembly when the LLVM IR was compiled back to the to assembly using Clang. In other words, they pass the round tripping test. These numbers are near 0 for Code Llama or GPT-4. So it tells us that training is helping. So to summarize, overall 96% compiles, 96% of the output compiles, and 20% exact match for compiler emulation, and 14% round trip match for disassembly or decompilation. These are both very promising results. But there are also significant macro opportunities for improvement in this space. First, these requirements of exact and round trip matches are too strict. Instead, we need a way to check the semantic equivalence match. Second, the LLM is used in a one-shot input-output setting, and there is no feedback to the LLM from the equivalence check. These seem like obvious areas of improvement. Because all these synthesis strategies are noisy, there is a need to validate the proposed optimizations. This validator is also called an equivalence checker. The equivalence checker must be sound. That is, it must return true only if the problem and solution programs are equivalent. However, it is hard to have an equivalence checker that is both sound and complete at the same time. In other words, the equivalence checker may return false even if the programs were equivalent. That is, it may have false negatives. The more robust an equivalence checker, that is, the fewer times it has false negatives, the more optimizations the superoptimizer can potentially learn. Thus, the power of a superoptimizer is in a big way dependent on the capabilities of the equivalence checker. For example, if an equivalence checker incorrectly discards a valid solution, our system will never be able to identify and learn the corresponding optimization, no matter how good our inductive synthesis algorithm or LLM is. As a recap, the full picture of a superoptimizer includes an equivalence checker that iteratively interacts with the inductive synthesis algorithm to eventually produce a solution. Recall that we said that the capabilities of the equivalence checker determine the power of a superoptimizer based development approach. The equivalence checker needs to support checks for end-to-end equivalence between an unoptimized program specification and a fully optimized implementation without assuming any knowledge of the intermediate steps used in the transformation pipeline. That is, it should be black box. It needs to support loops, aliasing information, floating point, and all the general constructs of an imperative programming language, such as function calls. The transformations it supports should include loop transformations like splitting, peeling, unrolling, unswitching, vectorization, etc. It should model memory precisely, including the presence of the ampersand operator, the address of operator, in the source code. Importantly, the equivalence checker must have no false positives. In other words, it must return true for truly equivalent programs. In other words, the equivalence checker must be sound. A false negative is a situation where an equivalence checker returns false when the programs are actually equivalent. It is perhaps not possible to build an equivalence checker that is both sound and has zero false negatives, because the problem is undecidable in general. The equivalence checker should aim to minimize such false negatives. This problem of equivalence checking has a well-known and important application in translation validation. Because compilers are so complex and may have bugs, a translation validator checks the source code against the machine code for equivalence. Because this is a well-understood experimental setting, we have been developing and testing our equivalence checker in this context too. Translation validation remains an open problem, and the development of an equivalence checker that performs automatic translation validation is a significant step forward in the development of provably correct compilers. Our research over the past many years has targeted this space, even though our broader motivations relate to a superoptimizer based compiler design. We have tested our equivalence checker against mature optimizing compilers on large programs. We have also tested it across aggressive vectorizing transformations, either implemented manually, like the strlen example that I showed you in the beginning, or through a compiler. Now I'm going to walk you through a demo of our translation validator. Consider this strlen function that I showed you on the previous slide, just that it is in the VS Code environment this time. And here is the optimized implementation as available in glibc. Our equivalence checker can be used to start an equivalence check. So for example, I can start an equivalence check and an equivalence check has started here. I just want you to quickly walk through the optimized implementation once again. The first loop here basically aligns PTR to a 4-byte boundary, or the boundary of the size of an unsigned long. The second loop reads a long word, which is 4 bytes on a 32-bit architecture. If it was a 64-bit architecture, it would have been 8 bytes. And then checks whether, and does some clever tricks to basically check whether those 4 bytes contain a null byte anywhere. If not, then we have saved a lot of work. We can just continue and load the next 4 bytes. So that's where the 3 to 4x speedup comes from. If it does, then it takes, then it checks which one is the one that is kind of, which of those bytes is the null byte, and then based on that returns the correct answer. Our equivalence checker completed while I was speaking, and it was able to find the proof, and I can view the proof here. The proof itself is represented as a lockstep correlation between the two programs. It encodes the fact that what happens if one program takes one path. So for example, this edge says that if the optimized program goes from the beginning of the program to the head of the first loop, then the unoptimized program also goes from the beginning to the head of its only loop. It also kind of encodes the invariance at this point. For example, it will encode the fact that PTR is equal to P when the two programs are at these respective stages. Then this edge basically says that one iteration of the first loop is equivalent to one iteration of the loop on the unoptimized program. This edge here says that if the first loop itself returns, then the unoptimized program also returns. This edge says that if the optimized program exits from the first loop, which means it has aligned to the 4-byte boundary and goes to the second loop, then the first program does nothing. It just stays at S6, the source line number 6. This edge says that one iteration of the optimized loop is equivalent to 4 iterations of the unoptimized loop, and you are able to identify relations, invariance between the two. For example, PTR is equal to P. And finally, if the second loop exits, then the first loop exits with less than equal to 4 iterations. Now, I've shown you an example of source to source equivalence checking, but we are able to do source to assembly equivalence checking as well. And I'm not going to run it, but I'd run it before I started the talk. And here is an example of a program that that is basically heavily vectorized. So on the left is a program that's taken from the test suite of vectorizing benchmarks. It has a loop, it has multiple if then else's and memory accesses and things like that. And on the right is the optimized assembly, highly vectorized, generated by GCC. As you can see, it has lots of vector opcodes that it's using. It's actually pretty hard for a human to ascertain that these two programs are equivalent, but it's only a matter of minutes for the tool to kind of see that these two are equivalent. And once again, we have a correlation graph that encodes the lockstep correlation and the invariance between these two programs. So for example, this one loop in the assembly program is equivalent to 4 iterations of the C program. Thank you. Over the years, we have found several bugs in compilers and other software such as the QEMU binary translator, a C libraries, and an SMT solver. All these bugs were found using our equivalence checker. In all these cases, when an expected equivalence proof failed, we tried to identify the reason for the failure. We would typically expect a shortcoming of our tool when there is a failure of equivalence, because as I said, the tool is not complete it is possible that the programs are actually equivalent, but our tool just couldn't find the equivalence proof. But sometimes we found that the bug was not in our tool, or the incompleteness was not in our tool, but there was actually a bug in the programs that we were testing. Except the GCC bug that is shown on the slide, all other bugs were previously unknown and were fixed immediately upon reporting by us. Some of these bugs were found by comparing implementations of the same function, for example, strchr, across different library implementations. For example, we would compare glibc with klibc and so on. Different people optimize differently, they write their code differently, and so on. And it turns out that some of these different implementations, as a result, are different. And when two implementations are different, as reported by our equivalence checker, then we basically check what is what is the reason that they are different, and sometimes we find a bug. I want to point out that these kind of bugs that we found were always very, very subtle. And the reason for that is because we are actually not searching for a bug. We are not searching for a known pattern of a bug. We don't even know what kind of bugs can exist. We are searching for a correctness proof. And when a proof fails, then we start debugging and we find, and it takes us some time to figure out, okay, this is the reason why they are inequivalent. And so the bugs are usually very, very surprising, even for the people who are running the tool or are developing the tool. Here is an example of a bug report where we mention the library and the example input which triggers the bug. For example, this report says, I'm writing to report a bug. Here is an example. And this bug was found in the strchr function in the klibc library, which ships with the Linux kernel. Now, sometimes, and these are the kind of responses that we will get. People will either fix the bug themselves, or they will thank us for a submitted patch. This is an example bug that shows the kind of mistakes that were caught by the equivalence checker. These mistakes were identified by comparing the equivalence of two library implementations of the same function across different libraries. Here is the function strchr, and it deviates from its specification if the character being searched is null. So if you call strchr with the null character, then the implementation is incorrect. Now, many testing methods will not even try a null character, and that's probably why this implementation kind of slipped through for many years. And this is the patch. Instead of using a while, you start using a for, and you add a break statement in the middle, and that's what they did. And here is an example reaction. For example, we reported a bug in the swap function of the netbsd library, and the bug author says that the previous optimization was incorrectly tested for over 2 decades and broken for years. Among other things, I hope these results convince you about the value of formal verification and the inadequacy of testing. To conclude, I hope we all agree that there is significant scope of improvement in compilers. And given the recent advances, a super optimization or AI-based compilation is perhaps around the corner. In future work, I think there is lots of work to be done in training the neural network to learn optimization patterns within a compiler, and there are multiple directions that can be taken. And there's lots of work to be done on the equivalence checker front as well. These are the references I'm using for this material presented in the talk. Some of these papers are in the public domain, not necessarily from our group. The equivalence checking work has been through multiple PhD theses in our group, and they're available as shown on the website. Thank you.
Hello, I'm Prajwal. I'm still an undergrad student, so please, I do apologize if I say something wrong. But obviously, we saw the bug reports, and it's clear that it's catching errors that people didn't think of or didn't test formally for, right? But like we're talking about compilers here, and no matter what code you write, it's brought down to a very definitive system, right? where it's a predictable system. So why haven't formal methods of verification not caught these errors? Do you think it's because of the testing methods that were used to verify these programs, or what is it that the LLM that you're using is catching all these bug reports that the formal methods could not? And is there a way that we don't let this happen again?
I just want to clarify, maybe I don't understand the question. So our tool is a formal verification tool, right? The translation validator is a formal verification tool. And all the methods that have been used to test these libraries, pretty much all the code that's written today, is usually not formal verification. They use testing.
Okay, then I misspoke. What I meant to ask was like, you can emulate these outputs or whatever it is into a very
May I request you to
I'll
get
get
your
it
question
offline.
and
Yeah,
take
yeah.
it offline in the interview.
So thank you for the excellent talk. I'm Sujit from IIT Bangalore. My question is about the superoptimizer loop, and I'm concerned about the gap that is left in the where we are not able to prove the equivalence. How much effort or how much compute is required to bridge that gap? Because that will decide the final success of this methodology. Even if it is 98% correct,
That's great. Yeah.
you know,
That's a great question. Thank you for that question. So let me just repeat the question just so that everybody understands. So the question is that I already said that an equivalence checker cannot be both sound and complete. It needs to be sound for the compiler to be correct, but it may not be complete, which means sometimes the optimization was correct, but the equivalence checker just couldn't find the proof. And because of that, we miss on the optimizations. And is that a fundamental weakness that is kind of going to cause the super optimizer architecture to fail maybe in the future? Well, I think what is our competition? The competition are current compilers. And as long as the equivalence checker can do whatever, can check and prove the transformations that are generated by the current compilers, we have already made progress. Of course, the problem can never be solved completely. Compilation itself is an undecidable problem. And so there is no hope of solving the problem in its completest form. But if you are making progress, that's good enough. And I definitely think that writing a translation validator is is orders of magnitude easier than writing a compiler. For example, the equivalence checker that I presented today is an effort of around, let's say, 20, 30 man years, person years. Whereas a compiler like GCC, which we are testing against our equivalence checker, is thousands or hundreds of thousands of man years. So definitely this is an easier way of doing things.
Hi Sorav, can you hear me? So I'm Ramit. I had one question. So the equivalence checker tool, is this ESBMC?
Is this?
ESBMC or like ESBMC? So CBMC, ESBMC, these are the tools.
No, this is our own equivalence.
Your own equivalence.
This is completely our own equivalence checker.
The second question is like, so you're already in the undecidable territory. So you're talking about syntactic equivalence. Can we go to semantic equivalence of two programs?
No, this is not syntactic equivalence. We are doing semantic equivalence.
You are doing semantic equivalence.
We are doing semantic equivalence.
Okay, then I'm good. Yeah, thank you.
Sure.
So I think partially my question is asked by Sujit and Ravindra, but I want. My question is, how do you give that specification to super optimization, and what is the specification again? Secondly, since the equivalent checker, I think this question is asked by Sujit. It has to be sound and complete. What is it if it is not complete? In your case, it is not complete. Are we going to not optimize fully, or what is its effect?
Yeah, so the first question is, what is the specification to the super optimizer? The specification is just like the source code, right? So you just give in the source code.
Okay.
But I think I understand your question a little better now. So basically, the idea is, I haven't gone into the full details of how the super optimizer is architected and things like that. That's available in the literature. Just for the paucity of time, I couldn't. But basically, we think of it as a pattern replacement matching thing. So think of it like peephole optimizations. So if you're aware of peephole optimizations, you have a pattern and you have a replacement. But this time, these are not like small peepholes. These are large peepholes that can contain loops and things like that. So we think of this. So we basically organize this as a peephole optimizer, and we'll have a super optimizer that learns these peephole optimizations over time. And then we organize these peephole optimizations as a table, index table. And then when you want to optimize something, then you basically query this peephole table and then kind of optimize it using Windows. And then we have an algorithm that kind of stitches them together using dynamic programming. So that's basically the overall mechanism. The second question is about completeness. As I said, I mean, we just need to be better than current compilers. Our current compilers are also not perfect. So. We just don't get the best possible code. Yes.
Great talk, Sorav. Thank you very much.
Thank you, sir.
So the question that I have is the equivalence checking that you're doing. Is it intra-procedural? Does it account for procedure calls in between? Can you take effect of compositions of procedures?
Yes. Okay. Great question. Our equivalence checker can certainly deal with procedure calls and all that. Inlining is something that is only supported partially right now, but I don't think it's a major, I mean, it's not a conceptual issue. It's more like an implementation issue. We can easily support inlining.
Okay.
Hi, I'm Prakash from Waymo. Thanks a lot for the talk. It was very interesting. So my question is more of, like, there's a lot of great work in like vectorizing compilers and scalar compilers. Have you ever thought of ML or AI sort of compilers where they're actually compiling for, like, say, GPUs or ML accelerators, where a lot of things are about numerics, quantization, and other things where you may want to, like, localize things where, like, numerics changes. Yeah.
Absolutely. Yeah, I mean, so AI compilers are very active today. Have we thought about it? Yes. Have we done something about it? Not yet. So one of the big applications of our equivalence checker, I mean, it's basically like this, right? So we have a large vision that we want to kind of get to the Superoptimizer, but we need to have milestones in the middle and kind of find applications, the most important application for what we have right now, so that, you know, we have some user base and we have some resources to kind of take this forward and things like that. Our current most fit for the kind of thing that we have done so far is basically safety critical sectors. I don't think that, you know, the AI compilers are terribly concerned about correctness at this point so much. But if you are, I'm very happy to talk to you, and yeah, we would love to support it.
One last question from Arvind there.
Hi, I'm Arvind. So I had one question on false negatives. So what classes of programs are actually harder to verify within the restrictions that you had?
Okay, very good question. If you look at my future work slide, so the question is, what categories of optimizations are harder to verify when I talk about false negatives? If you look at the last bullet here, support non-bisimilar transformations like loop fusion, polyhedral transformations. So the mechanism for equivalence proofs that I showed you was through a lockstep correlation, where I expect that one lockstep of one program is equivalent to some locksteps of the other program. And this mechanism works only for transformations that are, the technical term is bisimilar or lockstep preserving. And most transformations that a compiler does, like all the loops with peeling, unrolling, vectorization, are bisimilar. But there are these transformations like polyhedral transformations and fusion and things like that, which are non-bisimilar, and they are harder to do. And this is something that we have started on, but I think it's a long journey ahead to kind of do these kind of things.
Okay.
Thank you.
Let's thank Sorav once again. Thank you, Sorav, for an exciting talk.
Thank you for having me again.